Really not very straight. Does that look straight?
Straight, right?
Yeah, I don't know. It's just very hard to decide.
He's not down.
Okay, that's closer. Okay.
He asked Professor Nicole, do you know this movie?
Okay.
And then he's
All right. So let's get started. So I'm going to finish up what we were talking about with 3D waves, plane waves, and introduce briefly spherical and cylindrical waves. And then we'll talk about rays, just how they relate to waves, because that's the first sort of half of this course. First, at least 1/3 of the course is going to be about ray optics, which we discussed in lecture 1 or 2 at this point, like what are the differences between wave and ray optics, and which regimes that ray optics is more important. And after that, I want to start by introducing the interaction of light with matter. Again, at a very qualitative level, physical pictures only. There's almost no math that I'll be talking about, but I think it's very interesting and a helpful topic because that will then allow us to think about refractive index and how refractive index is related to the interaction of light with matter. And if we have time today, which I don't think we will, we'll get to the wave picture for reflection and refraction and discuss that. Okay, so in the last class, I quickly review, we introduced plane waves. The surface joining all points of equal phase, remember, is called the phase front or a wave front. And these, in our case, these are planar waves at first, right? So these are planes. And these are solutions to the 3D wave equation, okay? And these plane waves, typically you can think about it as if the symmetry of the source is such that it radiates in a planar fashion, then the waves will be planar, or even if the waves look spherical or cylindrical, when you go far away from the source, then they'll again start to look more planar, okay? We haven't talked about the sources at all of electromagnetic waves, but assume there's some source of light, the sun, stars, some light bulb that's far away, or a laser that's far away. All of those will look like they have plane wavefronts when you're looking at them when they're sufficiently far from that source. Okay. And we wrote down the equation for a harmonic plane wave, A sine k dot r minus omega t, where k is the again our propagation vector now. It's more than just a simple number. It's 2 pi over lambda times some unit vector, which is along the direction of propagation as shown over here. Okay. And as we saw in the last class, as I said, like as the time increases, so if I look at the plane wave at time t equal to 0 at one position, t equal to 0, then after some time, say t equal to 8, that same wavefront or phase would have moved over by a distance lambda over 8, 3t over 8, it would move to 3 lambda over 8 because the wave is propagating with the velocity of lambda times the frequency, or lambda divided by the time period t. And so, it moves in sync with that time. Okay, so that was about waves, plane waves. And as I said, they are solutions of the 3D wave equation, which is just a generalization of the 1D, right? It's just this equation on the left-hand side equals 1 over v squared, dou squared psi over dou t squared. And that is again represented by this operator del squared. Have you seen this operator del squared in any of your vector calculus classes, perhaps? So del squared is just a symbol for, looks like several of you have, but if you haven't, it's just a symbol for dou squared over dou x squared plus dou squared over dou y squared plus dou squared over dou z squared, sort of like acting like an operator on the function side. So del squared by itself has no meaning until it operates on a function, say psi in this case. And so we're just essentially, shortening, writing down all these terms as just one term. Del squared psi over is equal to 1 over v squared, dou squared psi over dou t squared. Okay. And sorry, backwards. That is the most general solution. Again, you can write down the solution by just thinking about, okay, we already saw in one dimension, the general solution to the wave equation was f of x minus vt plus some function g of x plus vt. Sorry, this should be plus. Sorry about that. Okay. There should be a plus there. I can't fix it right now, but please note it down. I'll fix it later. So the point is that we can always write down the solution now in 3 dimensions by taking that x and converting it to k dot r and minus and the k dot r is being written in this way as a unit vector k divided by the magnitude of k. Okay, just to show you that it's along some unit vector. The unit vector here is vector k divided by magnitude of k. Okay. So this is like the 3-dimensional analog of the 1D solution that you've seen before. Okay. And so the functions f and g, of course, can be anything we want. We saw like example, like if you have just some peaked function, you can like imagine propagating it in time to the right or the left, and that will still remain a solution of the wave equation if it is a solution at time t equal to 0. Okay. So as a small homework that you can do, you take this function f alpha x plus beta gamma alpha x plus beta gamma y plus gamma z minus vt, where these alpha beta gamma satisfy this equation. And what I want you to do eventually is substitute that into the wave equation and do the differentiations and show that this will indeed satisfy the wave equation, the 3D wave equation. It's fairly straightforward. I'll put up the assignment by the end of, it'll be due by the end of the next, meaning before the beginning of the next class. Okay, that's on Wednesday. So you have more than enough time. Okay, so now I move on to spherical 3D waves. So, so we extend the 2D, remember the 2D circular waves when we drop like, if there's a drop of water in a pond, you see ripples spreading out circularly from that source. In the same way, you could imagine that if you took a very large ocean and you dropped a little sonar buoy inside and let that buoy expand and contract, then what will the waves look like coming out of that buoy? It'll look like spherical waves if it was deep underwater, right? That's what you can picture, that's how the spherical waves would look like, because they're just on the scale of the ocean, that little buoy is like a point source, essentially. The same thing with light. Okay, so any object which is sufficiently far away looks like a point source of light. So you can again picture that point, so say it's a sun, it's a bulb, viewed sufficiently far away, etc. All of them, if they are sufficiently far away, they can look like spherical waves. And then as you get, as I said, if you're sufficiently far away, you can also think of like some small section of that spherical wave as looking like a plane wave. But the actual solution for a point source would be a spherical wave, because there's nothing to differentiate one direction from the other, so all the directions equivalent, so that looks like a spherical wave. Okay.
So in one case, so we have the property like a Bessel function.
We will come to that. Okay. All right. So the source is then said to be isotropic, and the wavefronts are just concentric spheres that are increasing in diameter. Okay. And we can understand this a little better by taking that wave equation and writing it down in spherical polar coordinates. So if, again, I'm not going through all the math of this, it's not too important for this course, but a quick refresher of spherical polar coordinates for those of you who might have forgotten. If you take any point P in 3 dimensions, and here's the X, Y, there's the X, Y, and Z axes, Now, instead of representing it as coordinates x, y, and z, you can represent it by three numbers, right? You have three numbers, x, y, and z. But instead of writing it as x, y, and z, we write it as one number and two angles. It's kind of like being, latitude and longitude on Earth. We have two numbers. That's because we are fixed to the surface of the Earth. So the radius is known, because we can think of the Earth as a perfect sphere. Then the radius is known and it's not changing. So then we have just two numbers, theta and phi, which are the latitude and the longitude. That's exactly what this is. So r, theta, and phi. And then we can rewrite x, y, and z in terms of r, theta, and phi, of course, but I'm not going through that math. And the idea is that then when you do that, you can write down that same del squared operator that we wrote down, which is dou squared over dou x squared, dou squared over dou y squared, plus dou squared over dou z squared. I can write that in this form. Okay, and again, skipping all the details, it turns out that in spherical symmetry, since the solution cannot depend on the angles theta and phi, meaning everything looks the same no matter what angle I rotate by. So if I rotated the whole sphere by some angle, arbitrary angle, the solution should look the same, right? In spherical symmetry. If there was truly nothing to distinguish one direction from the other, then the only solution or the only differential equation that gets left behind is this one. Dou squared over dou r squared times r psi plus 1 is equal to 1 over v squared dou squared over dou t squared times r psi of r psi. Okay, where psi is the wave. Now, and of course, remember again, going back to sort of, the psi, I keep saying psi, you can think of it as the electric field, for example. The electric field is like the of an electromagnetic wave of light is essentially the psi. Okay. And okay, so we already wrote down the solution for this. So if this was dou squared psi or dou x squared, so instead of x, replace it by r, and instead of the old psi, we have a new psi prime, which is just r times psi. Okay, so the solution then is just taking the usual solution for a 1D wave equation. The 1D wave equation solution was C1f of x minus vt plus C2g of x plus vt. But now because of the r psi, because now the wave equation is written not for psi but for r psi, then we get the divided by r. So we divide out by r. Okay. Obviously, the solution might look like it will blow up at r equal to 0. So we have to be careful about not going exactly to r equal to 0. That's because r equal to 0 is, of course, where the source is sitting, and that's a singularity for this particular wave function or for this wave equation. And that's just because that's where the source is. Okay, so we can't shrink this all the way down to 0, but we can take some small neighborhood around 0, and from then onwards, the solution will be good. Okay. So anyway, so that's our solution, the most general solution. So we see right away that if C1 and C2 are just constants, then the solution, and let's say for now we neglect the r plus vt because that represents a wave traveling inward towards the origin from infinity, whereas r minus vt will represent a wave traveling outward from the origin. So typically that's what we are more interested in, not in the wave that's coming toward the origin, but the wave that's going away from the origin. And so in that case, we see that it goes as C1 divided by R times F of R minus Vt. So we see that the amplitude of this wave decreases as 1 over R as you go further away from the origin. Okay. And so that's represented here. You get some amplitude divided by R. And of course, for a harmonic wave, this function F would be just a cosine or a sine. Okay. So that can be cosine. And you can, again, as I said, neglect the plus sign. Is just the minus sign for outward going harmonic waves. Okay. And the constant in front would be just the strength of the source, basically. Okay. And we have already shown, by the math, we see that if this solution goes as 1 over R, basically. The amplitude in front of that cosine function goes as 1 over R. But we can also show this from energy conservation. Okay, so let me just talk about that a little bit, which we haven't discussed too much, but I'll quickly motivate it. Well, again, I'm going to state some things without proof, or I'll just motivate it physically, and we'll see what the consequence of it is mathematically. So let's think about, say, the electric field, right? So we've said all along, light is just an electromagnetic wave, and in fact, the part that usually matters for most things is the electric field. Again, I'm saying this without any proof, but just take it from me for now that E, the electric field, is what is most important. Then you know from your sort of undergraduate electromagnetism, the first course, that the energy in the electric field can be written as half epsilon naught E squared. Okay. You may recall this if you remember something about like capacitors and how much energy is stored in a capacitor or in the electric field in a capacitor, then you can write this as epsilon naught E squared. Just if you don't recall, just go back and look at it. Does everybody sort of vaguely remember this expression? Okay, if not, you may have to go back and review that. But so again, we can see that the energy in the field is proportional, U is proportional to E squared. Okay. And so in that same way, the if you take the wave equation, we see that the energy that is coming out, it turns out that what matters in a wave is something called the Poynting vector. I'll come back to that when we discuss electromagnetic waves in more detail. But again, from that, you can show that the flux, that is the flux density, really, careful, which is defined as the energy per unit time per unit area. And another word for this is also the intensity or irradiance. Okay, all of these are roughly equivalent. I mean, you have to be a little bit careful when you're doing radiometry, but we'll just take it for now that this is. So this is often given the symbol I, which you might have seen, and I is essentially the power per unit area, right? The power per area. Because energy per unit time is just the power, and power per unit area is the intensity or the irradiance. Everyone okay with this so far? So this intensity, it turns out, again, from that motivation of the energy density in the field is just proportional also to E squared, with some constants in front, which are related to C and epsilon naught, basically. Okay. So that we'll see the proof of that later, but this is all you need to know for now to motivate why the field is falling off as 1 over R. Okay. So now let's take some light source. Let's say take the sun. Okay. Okay. Then we know the sun is putting out so many watts per unit time, right? So many joules per unit time or per second, which is watts, right? It's got a finite amount of energy that is putting off every second, and that is this P, the power. Okay, so power, of course, is just energy per unit time, and that's got to be conserved, right? It can't, I mean, of course, not exactly all the time, but in some small amounts of time, it's certainly conserved. We know that there's obviously some fluctuations and so on, but we can assume that at this instant of time, so now if I draw a big sphere around the sun of radius R, okay, then because the intensity is equal to the power per unit area, which is 4 pi R squared. Okay, see that, right? And I also told you that E, right, the intensity is also proportional to E squared. Okay, so from these two facts, we right away see that this electric field, right, because if I were to integrate this intensity over the full area, now imagine I took some other sphere, right, over here of different radius R prime, which is greater than R, then intensity cannot remain the same, right? Because again, intensity integrated over that sphere must give me the same power P, okay? Therefore, the intensity must fall off, right, as I get further and further away by this argument, because it's P divided by 4 pi R squared, and P is constant, right? And therefore, E squared must be proportional to 1 over R squared. Means E is proportional to 1 over R. Okay? So this is the this is the sort of physical argument of why the electric field from a spherical source must fall off as 1 over r. Everyone okay with this? What? That's for an electrostatic field. Yeah, right. So that's the difference from electrostatics. For a single charge, the force is, of course, going as 1 over r squared from Coulomb's law. But that's not this situation. This is an electromagnetic wave. Okay. Yeah. So this is an electromagnetic wave, so the electric field has to go as 1 over r, not a 1 over r squared. This is a dipole radiation, so it has to go like this. It's different from electrostatics. Very good. I'm glad you brought that up. Because you might be thinking that, this is, looks very obvious, but when you think about electrostatics, you learn that electric field falls off as 1 over r squared. And now in electromagnetic waves, it falls off as 1 over r. Okay, so there is a difference. Okay, so all right. And this is just showing that the profile of the wave, whatever the profile of the wave, f could be anything, as we have discussed, for a sine wave, okay? But for any, if you wrote it as some function f, then as whatever it is, it keeps its shape, but just decreases in amplitude as 1 over. Okay, as you go further and further. Okay, now cylindrical waves. Well, here this equation is a bit more complicated. So what are cylindrical waves? Well, they come from things that are more linear in dimension. So instead of a point source, think about a line source. If you have a line source and what the waves would look like from that, it has cylindrical symmetry. Because if you rotate around the axis of the source, that cylinder, that's a cylinder, that has that symmetry of that cylinder. Okay. And this now brings in the Bessel functions that somebody was, Abraham was asking. So again, we're not going into the detail of this, but the solution to this wave equation, this is the wave equation once you write it down for cylindrical symmetry. Again, we're skipping all the details. And now the wave function goes as 1 over square root of it. Okay. And again, I put in cosine k r plus or minus v. We won't have too much to say again about the, about this until much later in the course when we might need to think about cylindrical waves. But for now, that's the knowledge that, there are some waves that look like cylindrical wavefronts. And this could be caused, as we'll see later on, when a plane wave is incident on a slit in an obstruction, like a screen, and then you cut a slit in it, then the waves that come out from it look like cylindrical surfaces. Okay, so having introduced cylindrical, all these different types of waves, now I want to tell you about rays. Okay, and why is that? Well, we've already talked about why rays are so useful. Whenever the dimensions of the equipment are large compared to the wavelength, then a lot of times we can just approximate the propagation of the electromagnetic waves, or to understand the behavior of the electromagnetic waves, we can just draw rays and understand what goes on with the with those waves. Okay, and so what are rays? Well, you remember back when we were talking about plane waves a few minutes ago, we represented the plane wavefronts like this in time. Well, now if I draw normals to the wavefronts, okay, these are the rays. The normal to the wavefront surface, that's the definition, really. It's just at any wavefront, you draw the normal to that wavefront, that is the ray. Okay. And for a plane wave, obviously all these rays are going to be parallel to each other. Okay. And they're also going to be parallel to K. The wave for a plane wave, the K vector and the rays are all going to be parallel to each other. Okay. And you can also think of the rays as being the trajectory of the photons. So if you go to the particle picture, then these are the trajectories that the photons are following as they move through space. And in fact, there is a whole approach to field theory, which involves studying this kind of trajectories and doing something called path integral formalism for the rays or for the trajectories of the particles that allows you to think about the whole electromagnetic field or quantized fields, for example. Okay, but again, that's for an advanced class. And now what if the surface is curved, right? We just saw spherical wavefronts or cylindrical wavefronts. Again, we just take at each wavefront, we draw the normals, okay? And we connect them, right? And so here, this point here and this point here, they're connected by this ray, which is normal to the surface. And you can see that now the rays look like they are diverging from some central point. Okay, so the spherical wavefront will have rays that are looking like they diverge from that spherical source, okay, from that point source, sorry. Okay, so some properties of rays, we'll come back to this when we do ray optics in more detail, but the basic idea is we're just drawing continuous and piecewise differentiable curves that are normal to the surfaces, and the rays trajectories, as we'll see, are such as to minimize something called the optical path, and we'll come back to this when I discuss Fermat's principle. But in free space, these trajectories are all just straight lines. Okay. So in vacuum, in free space, whatever, by free space, sometimes we also mean air. For example, the trajectories are just straight lines in those situations. But as you can see, the trajectories might be converging or diverging from some point, and also they can be appearing to be converging towards a point as well. Okay. Or they can be parallel and just straight, as shown on the top. Okay, so I just introduced rays. We'll come back to rays when we do ray optics. Okay, so for now, I want to move on to a second sort of topic for today. Now that we've introduced the ideas of waves, we want to talk about how waves and light interacts with matter. Okay, and we'll see, or we can understand this completely, the process of transmission of light or absorption of light, reflection of light or refraction of light, are all just manifestations of the process of scattering on a microscopic level. Okay, so scattering of light occurring on a microscopic level eventually leads to the things that we think of as very different phenomena. Everything from like why the sky is blue to why rays bend when a beam of light bends when it goes from a medium like air into a medium like glass or water. All of that can be explained by the picture of scattering of light from atoms or molecules on a microscopic level. So that's pretty cool, I think. And so what is the idea? Well, the very basic and simple idea that we will have in our mind always physically is that let's say that we have some plane wave coming in and hitting some particle or an atom or something. Well, the atom now serves as a source of spherical waves. Okay, and these spherical waves are now radiated in all directions, right? It's a spherical wave, so the rays are just coming out in all directions from this. And this wave now interferes with the original wave, the incident wave, and creates the new wave, which is the total sum of the incident wave plus the scattered. That's it, as simple as that. We're saying that everything, all of these phenomena can be explained by this simple principle that we're going to take the transmitted or whatever wave that we're observing as just the sum of the incident wave and the scattered light from an atom, molecule, etc. Okay, so for example, so one of the things that we should talk about then is something that's very famous. It's called Rayleigh or elastic scattering. And the idea of Rayleigh or elastic scattering is that if you have, say, atoms or molecules, then when white light, for example, is incident on the atoms or molecules of air, where they're very far apart, these air molecules, especially say in the atmosphere, they're very far spread out by several wavelengths of light. Then the light, when it hits each of these molecules, is again, as I showed in that picture, scattered as spherical wavefronts. And it turns out that we can show by simple dimensional arguments that we'll think about in a minute, that the intensity of the scattered light, remember the intensity is proportional to the scattered light squared, right? I just showed you that, or at least motivated that for you. It turns out that that's proportional to 1 over lambda to the 4th. Okay. So Rayleigh or elastic scattering, as it's called, is strongly dependent on wavelength. Why do I call this elastic scattering? It's like this. So think about the atoms or molecules that are in air, right? So we know that atoms have some quantized energy levels. Even if you don't know quantum mechanics, I'm sure in chemistry or something, you would have been introduced to the concept that atoms consist of like sharp energy levels, right? With like, you would have learned like 1s, 2p, and all those various different chemical names for the orbitals of an atom, okay? So the electronic transitions or the optical transitions that occur is when an electron in an atom or molecule goes from one orbital to another orbital. That's how we get light coming out of that atom, right? You know this, hopefully, okay. So if the light wavelength or the light frequency in this case is much smaller than the frequency of the transition between those orbitals, which is often the case for many common molecules like hydrogen, hydrogen maybe is not the most common, but oxygen, chlorine, etc. Most of the atoms that form up our atmosphere, certainly nitrogen, etc., the orbital transitions, that is the energy spacing between the orbitals of these atoms or even the molecules, is much larger than the frequency of the incident light. Okay, so the frequency that is required to say excite an electron from the outer orbital to the next outermost orbital, for example, of nitrogen or nitrogen molecules, etc., or oxygen molecules, that energy spacing or that frequency difference between those two orbitals is much greater than the frequency of visible light. Okay, so what that means is that we can think of what's going on is that it's not actually like the electron is making a transition from the ground state to the excited state of that atom or molecule, but instead it just causes the atom or molecule to vibrate a little. Okay, this is again, I'm making very sort of non-rigorous sort of argument, but it's kind of like a physical picture of what's happening inside the atom. Okay, so it sets up like a little vibration of the electrons. So the electrons can't go all the way to the next orbital, but they sort of shake a little bit in their wave function, in their orbital. So, and this shaking is at the frequency of the incident radiation, right? Because whatever incident radiation comes in, the electron is a charge, is going to see that the incident electromagnetic field is vibrating at some frequency, omega, which we have talked about the frequencies in the 10 to the 14 hertz is the typical frequency of visible light, right? So now the electron is shaking at that frequency. And when it shakes, by Maxwell's equations, a vibrating charge gives rise to radiation, which is the scattered wave that I'm talking about. And so this vibrating charge cloud, or whatever you want to picturize it as, is giving rise to electromagnetic waves that are coming up. Okay? And in fact, we can model, and this is in fact one of the first simplest models that was written down for the interaction of light with matter, which is called the Lorentz model. Okay? And all it says is, I can write down the equation of motion of the electrons as a harmonic oscillator driven by the external field, which is the electric field of the electromagnetic. And from this, we were able to derive a lot of powerful results about refractive index, for example, okay? Which I'll come to in a minute. But this is the first I want to get the intuitive picture into your head. Okay, this is what was the model. The first model that was written down was we'll just write down that we'll picture, because they didn't know what was going on inside an atom. Right? This is like, 1800s. Okay. So they said that, well, what's happening is that the electrons the negative particles in the atom are like just vibrating, and they are behaving like a harmonic oscillator that's being kicked or being driven by an external force. That external force, of course, proportional to the charge of the electron times the electric field, and then of course cosine omega t, for example, where omega is the frequency. Okay. And in a minute, I'll come to why this Rayleigh scattering. So this elastic scattering is strongly dependent on the wavelength. As I said, it's proportional to 1 over lambda over 4. Okay. And this explained a lot of things right away. Okay. For example, the sky is blue. Okay. Why is the sky blue? We can kind of see it over here. So here's the sort of the upper atmosphere over here. Okay. The sunlight is going through, and let's say we're sitting here in Pittsburgh, right here. And as the sun goes through the upper atmosphere or scatters through all of that light, all that air molecules up there, blue light is being scattered large because it's 1 over lambda to the 4th. Remember that blue light, which is higher frequency, is shorter wavelength. It's closer to 400 nanometers or so is where blue light is. Okay. Whereas red light is closer to 700 nanometers, 633, 670, etc. These are all common laser wavelengths, for example. Anyway, so the intensity of light that is scattered in the blue region is going to be much more than in the red. So what happens is that blue light is more preferentially scattered out, okay, compared to the red and orange and yellow light. So the direct beam, of course, now will look reddish or orangish or yellowish, depending on various factors, how thick that atmosphere might be, etc. But blue light, which is strongly scattered out compared to those, will now be scattered out. And now we are over here looking up, we see that blue light being scattered into ours. Okay, so that's why the sky is blue. I think I've already talked about this. Atoms, molecules, so many things we can describe as just due to Rayleigh scattering. Tiny little fibers, hair, etc. Well, hair is probably too big, but because it's like a micron. Little bubbles inside, if they're smaller than a few, anything that has a dimension like smaller than lambda over 10, where lambda is the approximate wavelength. Let's take green light, for example. Green light is about 530 nanometers. Okay. So anything that's smaller than, say, or on the order of 50 nanometers, 100 nanometers, etc., will undergo Rayleigh scattering. Okay. So not only these kinds of particles. So of course, yeah, it's fine. You can say, well, that's fine for particles, but a lot of things we can't approximate them as particles. For example, once we get down a little bit down into the atmosphere, right? Or if you're looking at, say, some misty vapor or some gas, I can't always think of that as having, small particles that are independent of each other. But it turns out that even if you don't want to think about it as particles, if imagine you have a uniform fluid, okay? And now imagine that we're looking at small volumes within that fluid. Okay. As long as there are fluctuations, which there always happen to be some fluctuations of the density of the particles in that volume, say take a volume less than lambda over 10, for example, okay, then there's always going to be some fluctuations. Why? Temperature, right? Molecules are always coming in and out of that volume. So once you go to sufficiently small volume, these fluctuations become appreciable compared to, say, the number of molecules, right? Because the number of molecules is a certain amount, but then if it's a small volume, then the fluctuations can become comparable to the number of molecules. Again, they showed Einstein and Smoluchowski. In fact, this was during the so-called miracle year that Einstein had, when he came out with theory of relativity and photoelectric effect. He also, with Smoluchowski, showed this effect. Okay, this is also a very important relationship, that even some kind of density fluctuation in a small volume, and as long as it's rapidly changing, will have a similar dependence on the wavelength, 1 over lambda. So this Rayleigh scattering or elastic scattering applies not just to atoms and molecules, but even to things that we think of as more dense than just some spread out atoms or molecules. So what are other examples in nature? Well, things like the blue jay's feathers, they are blue because of scattering preferentially of blue light. Appearance of veins in your body. If you look at like small veins, they look more and more bluish. And that's again due to this kind of scattering. In fact, I think there's a whole bunch of phenomena that arise. Butterfly wings that are colored and so on. There's a lot of examples. I think one of the funny ones I thought was the butt of a baboon. Okay. I was like, okay, that's interesting. Maybe. All right. Okay. All right, so now this I think is interesting. Oh, wow. I've hardly gotten through any of the slides here. Okay. So, but let's take a few minutes about on this because I think it's a nice exercise. So, given that the scattered electric field must be proportional to the volume, and it must fall off like a spherical wave from the scatter. These are the two facts that you know. Okay, because of course we know that you have a slightly bigger amount of material in the volume from which the scattering is happening, then there should be more scattering, right? And similarly, it must fall off like a spherical wave. We already shown what that dependence looks like. It's 1 over r. From these two, can we show the dependence of Rayleigh scattering on wave? So why don't you talk to your neighbors a little bit and see if you can come up with a dimensional analysis argument. You all know dimensional analysis, right? So let's try to do that. So can everyone sort of, if you need to switch to your neighbor or something, like talk to them and say, okay, what is it that we need to write down here to get this scattering point for Rayleigh scattering?
I need to find.
So we have multiple groups, right? Let's take hints from each group. There are a group here. There are a group there. Yes, you have something to say?
Oh, no.
Your group?
We're agreed. It's easier to say that versus which is a really basic thing. That'll be ours.
See,
We're ready. We're agreed.
okay, all right. Again, we'll repeat the question. Okay, we will repeat it. Okay. So we have some small volume V, okay, from which there's some incident plane wave. Okay, so here are the plane waves, here are the rays coming in. We know there's scattered wave coming off. Call that ES, scattered light. Call this the incident light, EI. Okay. And I'm asking you to give me some relationship between ES and EI using these two facts that I've given you. One, the scattered light must be proportional to V, the volume, and it must be, if I call this the radius or distance from the scattered object, scattering object, then we know what that dependence looks like. It's a spherical wave. Given these two facts, what can I say about the relationship between ES and EI? Yes.
Say that it's scattered spirit
Yes.
and it's spread over.
Right. True. That is right. So, but is that the electric field that's equal to R cube or 1 over R cube?
No, just part.
Part of it. Yeah. Yes.
So the EM is
EM.
I'm the wave, right? The scattered wave
The scattered wave. Yes.
Sorry, yeah.
Yes.
is like it's 1 over R, right?
1 over R. Right. That's what I was. Exactly. It's spread out over 1 over R in this way. Right. We already saw that in the spherical wave. Can I call on a different group to tell me what the relationship is to the volume? Maybe a group over there. Groups want to volunteer. So I've written down one relationship, proportionality to R, 1 over R. I already told you it's proportional to volume. So the ES must be proportional to what? The volume, right? Yes. Okay. So from this, can I write down some relationship between ES and EI? Using dimensional analysis. And what will that give me for the proportionality between ES and E? Yes.
Oh no, wait, yeah. No. What are the units of ES?
What are the units of V? You should know this. What is V? Volume.
Oh, V is R would be meter squared or R squared.
R squared. Yeah. R cube.
R, yeah, sorry. Yeah. That's I don't get the V over R cube will get rid of the meters. I don't know if we need meters.
Yes.
How is E related? Power again?
The power is going as E squared. But we don't get to that. Power will go as E squared. You all remember dimensional analysis, correct? So we have to come up with some relation between ES and EI, and including the volume and the radius and some other constant or not constant, something that's.
But isn't the only way to relate CI and ES? I mean, we have to involve energy.
Why?
Isn't energy being absorbed by that little body and then
But this is dimensional analysis. Yes, you're right that if you start thinking about the physics of the problem, then there are lots of things to consider, such as the energy and so on. I'm saying this is how physicists think. I want to give you remind you that this is how we physicists have to think. Okay, sometimes we don't have to analyze the whole problem. We just have to come up with something that relates one to the other without having to go through all the details of the problem with our basic understanding of dimensions. Hold on, let's somebody back there raising their hand. Yes, Stephanie, right?
Yes.
Yes, please go ahead.
Or question.
Yeah.
That's.
Yeah.
Why is there? I just don't understand.
Why it is proportional? I guess this is again your physical intuition that as the volume of the scatterer becomes larger, the amount of scattered light must get larger. So we are just making a physical argument about what the dependence must be on that volume, right? So I'm giving you those two facts in some sense.
maybe ES is proportional.
Yes, and ES is of course proportional to EI. Very good, right? So can I construct from all this something that allows me to figure out the relationship between ES and EI? We have actually all the relations that you need to construct something for the relationship between ES and EI. Yes, Paul. Oh, actually, sorry. I'm sorry. What's your name again?
Jana.
Jana. Yes.
If ES is proportional to E and 1 to R and EI, I
Yeah.
guess we can write E as
Yes.
proportional to EI times 1 over R.
Excellent. That's what I was looking for. Perfect.
But I don't understand.
So, hold on.
Okay.
You're very excited. I'm happy. So ES over EI, what's the dimension of that? Dimensionless. Exactly. Proportional to V over R. Is this dimensionless? This is dimensional analysis, right? What's the dimension on this side? R squared, R cubed.
Oh, on that side. Sorry. You pointed to the.
I had to send you back
It's been a long
to
day.
first yeah. Volume is not R squared. You almost got me as well. So this is going to go, if we write the dimensional equation as L cubed, this is going to go as L, right? So there must be something, some other thing here, the proportionality constant, right, must have dimensions of what? 1 over? Yes? What do you say? Exactly. So K, so if I write this as KV over R, K must be proportional to 1 over L squared. And there's only one other dimension in the problem, or one other variable in the problem, which is the wavelength of light. So we argue that K must be proportional to 1 over lambda squared. Okay, so we have arrived at our conclusion that ES over EI, of course, there could be other constants and so on that will occur once you solve the problem accurately. But we can, without any further ado, say that this must be the general form of the problem of the answer right away, right? And of course, as he was pointing out, the energy, the intensity of the scattered light, which is proportional to ES squared, must therefore be now proportional to lambda to the fourth. So this is the argument for Rayleigh scattering, and that concludes my time. But in the next class, we'll talk about how refractive index comes about from these arguments. Okay, if you have any further questions, we can probably go. Yeah.